So it's, I mean, it's the same place. And it's a PDF.
Okay. Sweet.
I had it on
Nice. Thank you.
Thank you.
There's typos.
That's okay.
I got a lot of examples. I thought we could just do the examples in class. Maybe that way I can just keep going that one. And go through. Yeah, here's it. Treating y as a dependent variable and x as a dependent variable. That's a nice sentence. X should be in it. And in regression, I would drop that terminology and I would use y as response. Use usual.
So what would you say for X then?
Predict.
Predict.
I thought we could call y a predict e, but I didn't see anyone else use that. That's what it is, it's a predict e. But then I put some stuff on tomorrow. Experiments. There's theorems, but they're not for me. I toyed with the idea of calling things facts. But,
Yeah.
then I got supplements. That's where we're. So today it's continue with simple regression. And then Tuesday there will be a quiz. Folded samples to be on it, paired designs, correlation, discrete test for independence. Probably not regression because we just got stuck.
Can you read those four examples? Hair design.
Correlation. Discrete test for independence.
Any questions on that? Okay, so we've been talking about pair designs, and let's just do simple linear regression today. We'll look at two methods. We'll look at least-squares and Wilcox. And I'll talk a little bit about how to compute them. There's several ways we can go. Actually, now that I've got to the web, I can definitely use one way. There's a simple way, it's just drop and click. When you look at the page, you know you won't be doing that much more. Talk about that. Okay, so we have this model. We use the model last time. Our model is, so we're observing data like this. This is our data. And then we approximate the model. Right? And the model of interest would be a simple linear for today. And then we assume the model is good. In other words, you just assume that, and you're gonna identically distribute it, it's like a sample, random sample of errors. And there's a PDF running around. That's really the only assumption actually when we do Wilcoxon fit. There's only one very mild assumption. Finite feature information is all we need. But in this case, we don't. Okay. In particular, we don't have to assume the errors in the normal distribution. Okay, then the first procedure is the method of least squares, and in the book, actually in the book, Wilcoxon is much easier than least squares. I wanted to do them sort of in parallel, but I think notice as we talk in class, why don't we just do the regular least squares? I centered it. We can center things if we want to. We just change the definition. The slope doesn't change. So that's the centered line. In the book, and I call this X C on center. Again, in the old days, we would always do that. Okay? We would never calculate by hand without pre-center. But I think in my notes, maybe when I rewrite that part of the book, I'll just follow this model so I can make it more complicated by hand. Okay, so now we're after the linear model, and so just bring up a scatter plot in mind. So we have a scatter plot, and it sort of looks linear, right? Something like that. Now we're looking at lines that go through the data. And in my elementary stat classes, for at least one day, we do eyeball fits. All right, there's nothing big about trying to fit a line. You just need to get an estimate of slope and intercept. Right? And you can estimate the slope by eyeball. You know, this one looks pretty good. I call it an eyeball L1 because I pick out 2 points and fit a line through it. And then I can get the slope of the change in y over the change in x, right, between 2 points. That's my eyeball estimate of the slope, but then I need an intercept, so but I can always use the, if you have an equation to line. So I can eyeball that, and then I can just pick one of the points and solve it. This is not an elementary stat class, but that gives you an idea, right? It's not the most complicated thing in the world to come up with a fit, a straight line fit. Because, but if we all did eyeball fits, we'd have 30 different fits. So maybe it's better we look at fit procedure. And we certainly look at these squares. These squares, if you actually just add, it minimizes the sum of square root. So if you took an A and B, beta naught and beta 1, and that's the error you make. Okay, so this is the line I pick. So this line is beta naught plus beta 1 times xi, or x. And so here's the ith point. So this is xi. So this point here is xiyi, right? And that's the error I make, because I'm going to claim it goes through here, but really it's this point here. So this is y sub I, right, minus, it's going to be negative in this case, but it's going to be y sub I minus beta naught plus beta 1 times xi. So this is. So back here on this y-axis, this is yi, and this is beta naught plus beta 1. Is that true? So then you just minimize that. That's a deviation. This is a negative 1, and this is a positive 1. Those deviations should be handled the same. So now you can go to the method of Laplace, take the absolute value. So Laplace, what Laplace did. The computer had not been invented. Laplace took the wrong way. Gauss just put a square. You minimize the sum square. It's the average. A sum is an average. You just add, you're minimizing the average square root. You can see that's going to be disastrous if you have an outlier. Because if you have an outlier like this, that thing goes in squared, and that dominates the sum. To minimize that, the procedure really has to minimize that large outlier. And your picture just goes like this. You'll chase that outlier as it comes through. Now that lends itself to calculus because when the data come in, and then I think in the text I call this SS, center, now you have one data. Look. But you'll have the data, you'll have the x's and y's. So on the right-hand side, there's only two unknowns, beta naught and beta 1. So you can minimize that, and with a little bit of calculus, you can solve it, right? It's just, you just have to take the partial derivative with respect to beta naught, with respect to beta 1, and you set that equal to 0. That's a so-called normal equation, so you can solve it. So we know the answer by calculus. So we're trying to minimize. If you can calculus, you should be able to do this. So we'll come out to this. Actually, it's not too far from notation because you can rewrite this as, this is a bad way to write it because I have files done in code, but I could rewrite it like this. A different kind. It's just a weighted average. Then you can solve for beta at 0. But you can also do this. Suppose you just get beta at 1, and then the computer dies. How can you compute beta at 0? You can just look at the residuals, like pre-residuals, okay? So that don't want to hang a name on it. These would be the residuals. I've got the estimate of slope, these are my residuals. And then if you go back to the line, to the model, if you know beta 1, you could park this on the left side. And then all you have left is a location point, right? You have something on the left side equal to beta naught plus error. That's location. And in the book, I do go through location via the model. But that is location, so I know exactly what I'm going to do. I'm a least squares naught. So my beta half 0, I don't even hesitate, it's the arithmetic average. What's left, and you'll come out with y bar minus beta half 1 times x. And that's the least squares distance. Okay? Now, if you pre-center, you can show that it solves this equation. I'll leave it as that. See, that's a simple equation to solve. You just break this into two pieces. And divide by this, and break it into two pieces, and then solve for beta 1, and you'll come out with that thing on the top. These are least squares estimating equations. Not in common. Okay. Now, how do you, let's make a dumb data set and do it. Right? And we'll go through, I can't do many tabs. I'm sorry, I don't think I'll do that computer. I'm not going to get into another argument at all. Well, I should say. Let's just do a dumb data set. Let's just make a data set. How about something that's slope 2? It's not hard about the x's. You know, then in elementary stat, you may even go through the example by hand. There's shortcut equations. We don't have to do that in this class. I picked it. This is a nice textbook problem because x bar is 3. So x minus x bar is easy to get, and then you'd have multiply that by y for the numerator. It doesn't hurt to think of the schematic. I need that for my numerator, and I need this for my, and then there's the, I'll just have to add those two up. So you can fill out the schematic if you wanted to. But you know, you might have a problem with 1,000 observations. 3 digits of accuracy on guesses. So you never want to do that by hand. You wouldn't even want to do that by hand. I got an argument once with a math educator. I claimed that the hand calculator is like the slide. It should be thrown away. Just use a computer. So how can you do it? You can do it, let's go through with Minitab how you would do this. You would just enter these data points in C1 and C2. And then on the command line, you can click it too, you could just do regress. C2 with 1x, C1, this 1 stands for predictor. It's the number of predictors, not the sample size. You only have 1 predictor, right? And the predictors in C1, the responses in C2. That's it. Now, along with the fit, you probably want to get the residuals and the fitted values out, so you could do the residual plot, whatever. So just put a semicolon here, and then its fits. Well, I need to check this. I think it's this. And then resids. And follow that with the period. That's the end of my subcommands. And then I can, when you do this command, okay, you type that period and hit new line. It does the regression for you. It will come out with a table of coefficients. It will actually give you the regression line fit. Okay. And then you want to click on plot. If you want to do the residual plot, you just do plot. Right, this would be a clicker. You want to do line command plots. So you want to click on plot. Well, you've already done that, but you should have plotted the relationship. So it's a click. You click, and then you plot. You want to plot what? You want C1 on the vertical axis, right? So it's on C1 versus C2. And now you click plot, and you want the residuals on the vertical axis. That's what most people do. And the fits along the axis. Okay, so you already have 2 diagnostics, and you might as well do a box plot. You never want to do things by hand, right? So see if you have any outliers. Let's do a box plot. Actually, Minitab has an outlier role, and it will ID outliers for them. Look, we got the last table, I think. It's 3 or 4 tables. That's the bad thing about packages, right? They go on and on and on. Minitab used to really be bad in their days because it would give you the figure. Okay, that's one way. So this is Minitab. How about with R? With R, we can go through this with R, and LM comes with R, so you don't have to have another package. You will be. So, data today, so I don't have to get to the web. Because I can't depend on the machine. Okay, with R, you would just go into R and then you need the data in. If you're entering data by hand in R, I would just use the scan command. You can use equals or guess. You want to be sophisticated, you should use guess. People will be impressed. But then you can just put the data in. It's not. Okay, so our data is in. We could verify if we wanted to. We could plot it. Here's our big sum. It's only 5 here. Let's not worry about native running, just I might get there. Boy, what's your name or name? And then I would get used to storing the fits somewhere. Give it a name you might remember. It's just LM. And it's just Y with X. Tilde. And you want to do something with I'll give you the table. So there's your table coefficients. The stroke is 2 right on. Now this is a good textbook problem. That was just guessing. The intercept's 1.6. And we'll talk about these things in a moment. But anyways, those are the standard errors. So with a few assumptions, you can do confidence intervals immediately. Okay. And we'll talk about R squared in a few moments. And there's another test for slope. We talked about that yesterday. There's a natural null hypothesis, beta 1 equals 0. So that final F statistic is. But you can also do it with a T. So we'll talk about that. And you need the residuals. It's just residual fit. Yeah, that's understood. Oh, either or. So this one. So what you would plot y at. So it looks like it's a good fit. And again, you don't have to do it. You can destroy it. Let's have y be so typographic. Just do LM. It'll give you the coefficients. So you just increase the slope by a factor of 10. Of course, with 5 data points, it will cost less too much. So it's very sensitive, of course. But you do that on the way you drive. And then the final way, you can just drop and click. We'll look at that when we do the roll calls. Any questions on least squares so far? Oh, let's go over our square. Again, this is your model, right? And you want to know the contribution of beta 1. That's X, right? That's not, in fact, again, that's why we have that natural hypothesis. There's the only place X comes in the model. And so there's a very intuitive measure. It's probably the most widely used and probably the most abused. People really get excited about their own squares. But it's a very intuitive statistic, and it just begins. There's two things, and then we can compute our square. And they're both fits. The first is, I didn't know I had X. Okay, so you fit without X. Well, then the model is, well, it's just its location. And you're doing these squares, so you know what they have 0 is, 5R. Here's your fit. And then what's left? Well, this is the variation that's left. So this would be this is what's left. This is your estimate of variance. That's why we divide it. But that's the amount of variation. Right. If all the y's were the same, that SST would be 0. It's sometimes called total sums of squares. Well, you fit with X. What's left? Well, that's the residuals. If you want, it would be this. But that's the variation left. You haven't accounted for that variation. So the variation is accounted for by fitting X is just the difference. Sometimes this is called SSE, the sum of squared errors. So that's the variation you've accounted for. SSR is usually sums of squares due to regression. So That's the variation you have accounted for. This is what you started with before you got into number 2. This is what you ended up with. Okay, so this is what you have explained. And then R squared is just the percentage. R squared is just SSR over SST. Usually multiply by 1. So it's proportion of variation, percentage, explain variation. Now, as you fit more x's, more predictors, we hope this R squared goes up. But it'll be the same, okay? It's such a very intuitive statistic. No matter how many x's or predictors you have in the model, one is the same. It's like ground zero. And then number 2 is the same, but you fit all the x's. So it'll never change. I mean, you just add a bunch of x's. But this thing stays the same. This goes down forever. That's our square. Any question on that? Okay, so now we've done these squares. Let's do the Wilcox. I centered everything in the book for a reason, because at first the Wilcoxon just ignores those. Okay, so what's the Wilcoxon? Well, it's very similar to these squares. In geometry, you would say that's the norm square difference of 2 vectors. And for the Wilcoxon, you just change the norm. Another way to see it, or we don't have to do that in this class. You get an idea of why these squares gets messed up if you just write this sum of squares in 2 pieces. Just break it up. And this is your error from the regression line, right? And this is like the weight you've attached to it. Well, if you have an outlier, okay, this will be large, but you've attached a very large weight to it. It'll dominate the sum of squares. See, when we made that change from 11 to 110, then that fifth term became so big that to minimize the sum, you concentrated on that term. And you end up with a horrible fit. So, I mean, the scope was 20 instead of 2. Says, okay, yeah, we'll do it like that, except we'll put our own weight in there, and we just rank that first set, 1 to n, and then we assign a score to it. Now the score is like standardizing. It's kind of weird. But if you want to, you can just think of it doing that. You score it. The Wilcoxon comes by and just puts it on. And then it does normalization. Now something happens when you do the rank on these. That beta naught doesn't matter. That cannot change your rank. Okay? If I'm ranking observations, I want to rank these numbers from 1 to 4, right? What if you add 200? That would be the same ranks. So it doesn't matter. So that you can ignore the beta. And you can center the data, it won't matter. So oddly enough, it will fit the center data. Okay, because center data, you subtract off x bar, right? But that won't change the rank either. It's beta 1 times x bar. That's constant. The only time you get a change in rank is if you change one of the I things, yi or xi. So the estimate is beta 1 minimizing. And I'll give it some name because we're using it. This is the 80. So it minimizes that. And then what is A? A is a score. The phi is just a unit. These are the Wilcoxes. Now this phi is I over n plus 1, so it's only defined on 0, 1. And in this case, it's just this function. Well, this is goes through 0, 1/2, and this would be what? Right. Now the important thing in this is, why do we have this radical 12 here? Divide by n minus n plus 1? It won't matter, okay? But if I do that, the standard errors are simple to write out.
Something I learned about pregnancies.
What are the other constant? What? I said we don't need it anymore. I standardize things. The Wilcoxon is the only linear score function. And it's one people use because you don't have to think. It's just a linear score function. And if you do a 2-sample problem by regression, which we'll do later, we'll get the Mann-Whitney estimate. Now, how do you do that minimization? Well, that's another story. And you can actually use calculus. If you use calculus, when you take the partial, you just ignore the A. The whole A piece you can ignore. And then we'll get to the right answer. Okay, so that's beta hat 1. Now maybe I'll put a W. And then once beta hat 0, it's just a median and plus 1. Okay. So of course, if you need the computer to do this, you can't get this in the closed form. You can come down to the equations. The equations are sort of interesting. You can show it looks a lot like these squares, except you have the A. It might be an interval, so you usually put a dot. But that's what it solves, and these are the Wilcoxon. So it just solved that. But you can look into what it's solving. It's actually, it solves a decreasing step function. In the simple linear case, it is very intuitive because it's looking at this. Here's 0, and you have a decreasing step function. It's monotone, so here, this would be your solution right here, the same. That's actually what it's solving, and it steps at the sample slopes. See, there's slope in a problem, right? Here's the slopes. You just have n choose 2 of them. But that's what it's solving. That's where it steps down. So you can write a little trace routine if you want to. You just go through the sample slopes and find the estimate. It's not the median. It's close to the median, and there is an estimate called field estimate, which is the median of the slopes. I don't use this one because I can't do anything else with it. It becomes a mess if I do more than this. Okay?
Yeah.
So again, let's go through how we fit it. So we could go back to how we compute it. In mid-tab, you just put another R here. And that would give you the work cost.
R.
So you can do it with me. So it's RR, robust regression, that's what it stands for. And the syntax is the same. The output's not the same. I mean, it gives you both the Wilcoxon estimate, standard error, which I'm not very fond of. But this task, we can use that. Minitab, if that's the okay. The second way is you can do drop and click if you want to. Okay, there's RGLM page. It's like our webpage, fisher.stat.ww/Kremen.
It's not there.
It's up each word on the screen. /Kremen/Kremen. Kim is Kim Kremen. A student of mine. She really put this work together many years ago. Then I should see this. This is when I switched to our big time. It's hard to run the web at an institution. Because you have to follow their rules. But there's simple regressions in it. So you can do one sample, two sample in regression, but actually we can do one way and two way with the two if we want. I just can't do any multiple regression. while, we can use it. And then you just put the pressure in, I think it's X, Y. It says up here somewhere. Yeah, X, Y is in there. You can browse for a file too. If you have a large base. But for this one, we have this simple. So we can just put it in. Okay, so it's just X, Y, and it's white space separate. Then you can, there's all kind of plots you can do. Let's do this. Then you just now it comes back with the output. Actually, it was much different. It's only 5 data points, so don't get excited about it. Oh no, the slope is the same as 2. Let's look at the wrong blocks. In this case, we got the same answer. It comes back with side-by-side analysis, and for a while we've been pushing this. Okay. Then the third way is there's a couple R routines we can use. I like to use R fit. If you're going to do this by R, you have to get the pattern for fit. You have to drop in. Just type in Craigslist. Craigslist. But anyways, you want contributed packages on it. And it's our fit. There must be over 10,000 packages. This has become the language of statisticians. Just click on one. And then on fit. Then this comes up, and then you can pick the package. It depends on Linux is first, or Unix things. And then this is Mac, and this is Windows. There's a reference manual. You'll need Quant Reg too. It's in blue there. It's highlighted. You'll have to download that. I think it's still version 14. John Kobe's done a lot of this work. But you can download that, and then you have to install it. That's I don't think you can install it, but I think I have to look in it. We should be able to do it. Now I've installed it, so I can go through it. I have to bring it in. Once you've installed it, then you always have to run this again. It just adds that line. And I think Quant Grid comes in with it on there, but I think you still have to install Quant Grid. But the fit command is the same. Instead of LM, it's all fit. So here's fit will blocks on the data set. And it's the same syntax. And then you can do a summary on it. See, that's the same estimate as a web page. They may differ. The standard errors will definitely differ. I know that because I know how many tables standard errors. Oh wait, on the web, on Minitab they'll differ. On the web page, you'll be close. It should be close. Okay. Any questions on computing yet? And you can do residuals the same way. And on the y-hat too. Not quite as easy as anything, right? It'll be close to v squared. So the intercept is different. Okay? Then let's finish it while we have, we could go back and forth. If I bring the other one, we'll use Minitab. So there's another package you can, might be easy to work with. We could talk about that later. Any questions on that? You have to use a computer, okay? You can't use. No one does statistics by hand anymore. Here is a very fast idea, simple regression just for time. Mark it because we speeded it up by incorporating some old friction. So it's a simple regression model with 10,000 observations and random estimates and such. This is, we live in an age of very fast computers. It's faster and faster. I just can't believe it. I'm working with some people in CS on parallel computing. So the speed up there should be dramatic. Okay, if you go back to d squared is r squared, we proceed the same way with that d. Okay. It's the same algorithm. But here's the model. Here's the model. And if you fit without x, there's no x's in it. And that dispersion function, that d stands for dispersion, is invariant to beta norm. So it's just DOI. Okay. But we're actually already using it. but it's just this. Well, you can show this as a scale estimator when there's a big typo on the floor. I have it is, it's consistent for. It's a consistent estimator of if the errors are normal. It's a big F. Then it estimates sigma times a constant. The constant is, I think, 3 over 1. Yeah, here's the big type. Yes.
Okay.
I don't know if it surprises you that thing we wrote down as an estimate of sigma. Well, I have to divide by, or multiply by square root of 3 over 5. But it estimates sigma. Right? So it's a quicker estimate of sigma. It's not that, it won't be the standard deviation, you know, because it's estimating the same amount. Yeah. With that. So this is the amount of dispersion left, right? And then if you put X, the dispersion count. And then, so here's an R1. I remember, this was many years ago, or 30 years ago, that's old. I wrote that out in my office one day. I said, oh, this is what you need. Then I tried on some examples, and it didn't turn out to be neat. The problem is, that numerator is robust, but the denominator isn't. It's also on scale, okay? Your estimating scale is a consistent estimate of sigma, not sigma squared. So you have to be careful comparing this with r squared. They won't be about the same. And this one's not robust. So thank goodness r fit turns out the robust one, which I'll just put up here, and we'll talk more about this later. It has another denominator, and that's robust. The RD is the reduction.
Page 97.
RD is robust. The denominator is not robust. But you can patch it up. And I don't know if you know anything about R squared. Some of you might. You know, with R squared in a simple regression problem, you can manipulate R squared till you come out with the F statistic. And that's how I came up with this formula years ago. I did the same manipulation and it worked. So that comes out of our fit. So today we went over regression. We did least squares and Wilcoxon. And then least squares, you can put formulas down, but I don't ever see any of you ever using them, right? The computer does it for you. Unless you really have your hand calculator. And how about the Wilcoxon? Well, there aren't formulas, but the computer does it for you. So that's what you have to think of. We have a way of getting the information from the computer. We even have an analog of R squared. You use R squared when you compare models, and we'll talk a little bit about that. And that's the way you use this R2 also. You can use it for comparing models. Okay, so, what we need to do then is, we want to go over, on Tuesday, we want to go over standards a little bit, copy samples, and, a couple of odds and ends, like predicting, we should talk a little bit about that. And, then we'll go through some more examples. And then we'll be into multi-regression. And then we can start picking off the things we want to do, like 1 way, 2 ways, so. They're all in the models. We'll have the clues. Here's the basics.